Today we continued our investigation looking into the modified Atwood's machine lab, which looks at the variables of net force, acceleration, and mass of the system. Today we did part 3. In part 3 of our lab, we used the same cart, string, hanger, and photo gate setup that we had before. Groups were careful to make sure that the track was frictionless going towards the pulley, and found the masses of the cart, string, and hanger, and 3 extra bar masses, one of which was gray, 2 of which were black, and then the mass of the cart, string, and hanger as well. Today, we decided to look at seeing how changing the mass of the system would affect the acceleration when the net force acting on the system was held constant. In order to keep the net force constant, students figured out that they would have to keep the mass of the hanger the same because the net force is the weight of the hanger. In order to find the acceleration after each trial, the photo gate and smart pulley would work together to send position time data back to the computer, and from that they could build velocity versus time graphs, the slope of which were the accelerations. So after each trial, groups gathered 3 for each set of masses, groups found 3 accelerations that they averaged at a time later. In order to change the mass of the system without changing the net force, masses were added from outside the system onto the cart. So first, they ran the system with no additional masses. So you just had cart, string, and hanger, and they ran 3 trials, found the acceleration from the velocity versus time graph, and then to increase the mass of the system, they added a silver bar, which had a mass of about 250 grams extra, ran 3 trials. Oops, undo that. We then removed the gray mass and replaced it with a black bar, which had a mass of about, which had a mass of approximately 500 grams. And that's not grabbing very well. We can take that and put it on top. We ran 3 trials. Then students added the gray bar to that black bar. So we had about an additional 750 grams. And finally, the students removed, will it let me? Remove the gray mass and added a second black bar. So those 2 black bars together were about 1,000 grams of extra mass on the cart. Again, the whole time we did not change the net force. We didn't change the mass of the hanger so that the net force would remain the same. Then students moved towards graphing the data. Students wrote down the mass of the cart, string, and hanger, which that never changed, but they included the masses that they added. There's a place in the data table over here to add the mass of your silver bars and your black bars as well, and it was important to keep track of which black bar was black bar 1 and which one was 2. Most had letters or other indications to keep track because the black bars do have some variance. In order to find, once kids got their mass of their hangers in here and added in the masses that they added to it and put in their accelerations, they were ready to have the computer do some calculations for them. In order to find the mass of the system, you simply had to add the mass of the cart, string, and hanger to any additional masses that were in your system. And then if you click that in, I should have said, so we marked equals, we selected cell A, added cell B, and hit equals. When you do that, you might get a little green box that says, would you like to apply that to the rest of the column? In which case you can choose yes. But if not, see how the cell is still highlighted. You can grab that blue dot in the corner and it will apply that same formula, taking the sum of these 2 to make the mass of the system, the sum of these 2 to make the mass of the system, and so forth. Prior to starting the video, I had added in these fake accelerations for that, and then we'll have to find the average of the accelerations. There's at least 3 different ways to find acceleration using Google Sheets, but I find the easiest one is to open up this 3 dot, which will take us down to the sigma, which opens up a variety of calculations. We're going to choose average and simply going to average or select these 3 cells here, D2, E2, and F2, by clicking and dragging across the 3. You can see over here it's now selected D2 through F2, hit enter, and that's the average of those 3. Again, you might get the green box over here. If to say, do you want me to apply that to the whole column, you can choose yes, or drag the blue dot down and it will calculate all of the accelerations for you. At this point, you're going to need to select average acceleration and mass of the system. If you have a Chromebook, you'll need to select one of the columns and then use Control to click on the second column, or if you're on a Mac, the second one you hit Command to select the second column. Then we've got mass of the system and average acceleration selected. We're going to insert a chart. Really, that's the words they use to insert a graph. Once the graph shows up, I encourage you to make it small enough that it fits below the first 3 or 4 columns of our data table. I'm going to shrink this down so we can see a little more of this at one time. It's important to check out to make sure that what's showing up on the graph is really what's there. So right now, if I take a look at my biggest average acceleration is 1.7, so I'm going to look on my y-axis. Is my biggest value around 1.7? It is. And then I want to look at my biggest mass of the system. My biggest mass of the system is about 1.25, which that value is my biggest mass of the system as well. And it looks here like as the mass of the system got bigger, the acceleration got smaller. This is not the shape of any graph we've seen up until now. By the way, if you found that the units don't match up, like if 1.25 was your biggest value here and 1.7 was over here, if you double click on the graph or choose chart editor here, you're going to want to go to setup, double check and make sure you've got a scatter chart here instead of a line. You want to double check and make sure that what's on the x-axis is really what you want. Mass of the system is what we wanted. That was our independent variable. And then on the y-axis, we have our dependent variable acceleration. If you needed to switch, you can. These are toggle switches, so you can choose whatever you want, but it was correct the way we have it. At this point, we could go over to customize. If you needed to add a title for your chart, you can click here and type in the appropriate title. This is a toggle switch. You could later pick horizontal title to type in mass of the system in kilograms, or the vertical axis for average acceleration, but these all popped in there automatically for us. Again, you can do all of those through that same toggle switch. Next up, we're going to go down to series. Normally at this point we would have drawn some sort of a best fit line or best fit curve, but today we're going to draw a trend line. Unfortunately, that's not a line, right? As the mass got bigger, the acceleration got smaller. We call that an inverse relationship, or these are inversely proportional. Students today found that if they use the power series in here, that gave us the best fit curve for that data. Unfortunately, with the math that we know at this point, we don't know how to analyze a curve yet. So in order to do that, we're going to have to linearize this graph. Using the student guide to graphical analysis, we found out that if you have an x-axis, as the x-axis gets bigger, the y-axis gets smaller, that inverse relationship. If we make an acceleration versus 1 over the mass of the system, or acceleration versus the inverse of the mass of the system, it may linearize that data for you. So the next thing you're going to do is you're going to have to create a title for a new column, 1 divided by the mass of the system. And because the mass of the system is on the bottom of that fraction, it's in the denominator, when you put the units on this, it will be 1 over kilograms for the units. In order to calculate this column, we're literally going to put in a formula that represents pretty much the title. We're going to hit equals so that the computer does a calculation, select the number 1, use the / for divide, and then you're going to go over here to column C and select cell C2 where the mass of the system is. At that point, you can see over here the formula is equals 1 divided by, and the C2 is lit up because we selected that cell. Hit enter. You will probably get a small green box over here to say, would you like me to apply that to the rest of the column? If you do, great, click check. Otherwise, you can drag that blue dot down and it will calculate these values for you. So next up, we're trying to make an acceleration versus 1 over the mass of the system. This was our dependent variable, and this is the inverse of our independent variable. And again, we're going to insert a chart, which is giving us the graph. I'm going to go ahead and grab that and make it small enough that we can see that and the data at one time. Grab that and pull that over here. Now, unfortunately, we were trying to find something that was going to linearize this, but those look like curves as well. So we're going to have to do some manipulations with this. First of all, let's go to Setup and go into this and make sure that we're using a scatter plot. So we have scatter, and let's take a look and see what's supposed to be on the x-axis. The x-axis is supposed to be 1 over the mass of the system. So under x-axis, hit the toggle switch and let's choose 1 over the mass of the system. Under series, we want it to be acceleration. That's what's going to show up under the y-axis. It has that, but it also has selected 1 over the mass of the system. We don't want that, so we're going to choose these 3 dots here and remove any unnecessary variables from that. Now the graph's looking a little bit more like it's linear. It's a good idea at this time to double check and make sure values are appropriate. For instance, the x-axis is supposed to be 1 over the mass of the system, and looking up here, our biggest 1 over the mass of the system was about 3.8, and look here, that's 3.5, so that's good there. And our biggest acceleration, I think, was 1.7 in the 1.7 range, and that's acceleration, look over here, it's 1.7, so that's in a good place. I notice that we don't have names for the axes. We'll come back and do that in just a little bit. Under Customize, we're going to go ahead and go to Series and try to find a best fit line or find a slope for this. Again, we're going to go to Trend Line, but because this is a line, we can keep the linear. We don't have to select any other type of matching for our best fit. Go down to where it says Label None, and in here we're going to use the equation to find the slope. Most students today had slopes in the range of about 0.44 up to 0.49 for the units. Again, I'm sorry, for the value for the slope. Notice that the units don't show up in this program, so you'll have to figure those out on your own based on the variables units for the y-axis and x-axis. Speaking of which, we need to go ahead and make sure that the chart or this graph has the appropriate titles. So we're going to go into Chart, Titles, and Axes. The chart title looks good, average acceleration versus mass, 1 over the mass of the system. So that one works. For the horizontal axis, we're going to type in the title 1 over the mass of the system. And the units that went with that are kilograms. Oops, 1 over kilograms. And for the vertical axis, that would be average acceleration, and that would have been measured in meters per second. It's also okay to do the caret button, which is Shift 6 followed by a 2. That's meters per second squared, either considered acceptable. I'll click off on that. And at this time, I'm going to go ahead and close the chart editor. And again, we now have an acceleration versus mass of the system, where as the mass of the system increased, the acceleration decreased. Over here, we've got an acceleration versus 1 over the mass of the system with appropriate labels and units here and labels and units here. I noticed the y-intercept is very small, but it doesn't look small over here. We can take care of that again in the chart editor if we go over to Customize and then go down to where it says horizontal axis and just make the minimum value 0. Hit enter, and you can see immediately that made the y-intercept look 0. You can do it for the vertical axis as well, but I don't know that that's going to change the shape of our graph significantly at all. So I'm going to go ahead and close the chart editor, and tonight for homework you'll be answering questions about your 2 graphs. This is the first graph you made. If you're answering questions about the evaluate your graph or doing a mathematical analysis, most of those questions will be based on the shape and the slope and y-intercept of your acceleration versus the inverse of the mass of the system graph here. I hope that helps.